This call is now being recorded.
All right, cool.
This call is now having notes taken by me.
Okay. So I was just discussing what system design really is, and I was claiming that I'll just repeat it for the sake of it because I just started the video. So um, there's a lot of data to be computed right now. World is getting very data intensive. We want to scale components individually depending on the requirement. Either there is compute or there is data, not either or. It can be both of those things depending on the requirement. We might have more data, we might have more compute to be done, and this is the main problem of the system, main point of system design that we're trying to solve: how to make this fetching, storing of data faster or reliable and reliable slash or and unreliable, depending on the problem parameters, right? Somewhere we want more reliable data, somewhere fastness matters, somewhere writing is all that matters, somewhere reading is all that matters, somewhere write is greater than read. As in, what I mean by that is write speed is what matters more than the read, somewhere read speed matters more than the write. And all of this, depending on the requirement, all of that in the end finally helps us design a better design, a better system for us. That's the basic idea, right? And I was just giving the example of YouTube upload where the correctness matters more than how fast we write, right? In the upload case, right? Let's take another example, like, I don't know, maybe Zoom call, right? Where the number of connections is maybe matters to us more. Depends on what the requirements, what the initial requirements you make up, or what the requirements you discuss with your interviewer, right? This is how it's going to go, right? So at the very basic, we have, of course, a client, right? And an application server and a database. We always draw like this kind of. Okay. So this is like a very basic kind of, uh, very simple diagram kind of we have. This is the most basic thing. Like, this is for compute. This is for our data. And everybody understand what database is basically? Do people know what database is? And a lot of you might have very false assumptions about it, and that's also okay. We're gonna, of course, deal with it right now. So, what is database? Does everybody know about what database is, or nobody knows? Is it just so? Of course, okay, for answering, you can just answer right now. Like, unless if people want to raise hands, they can raise hands and then answer. Up to you. I don't mind. This is the compute server, like which takes in the request. Let's say I want to upload a video. So upload a video goes here, where this is some compute server, right? Like some application, some code is running over here, which basically processes the request, kind of, right? Where it processes the request, makes this connection, and then sends it out to the database to get this data from the database. Database is where the data is stored. But today I want to start from, basically I start from inside out always. What I mean by that is, like, because database is like the most critical component I feel of system design. So I spend most of my time here, and this is what the interviewer also kind of wants you to. Of course, the whole design matters, yes, and there are multiple components in it, but this is where we start from because this is like the most important thing, I feel, at least. Um, so what is database? I know it has data, but what do people have some opinions on it? People know about it? Anything? Anybody wants to say? Yeah. And speak out. It's okay. It doesn't matter if it's wrong. It's all good.
Organizing data,
Sorry, go on.
organizing
Organizing data. All right. How do we want to organize data?
uh,
So it is like managed via SQL and typically structured tables like rows and columns.
No, so structure is
Where
organizing. Got it. Why do we want to do it? Why do we want to organize data?
So it becomes easier for us when we want to fetch it.
Right. Same thing, right? So fetch, store is our main point, right? This is what we want to do. So, okay. Is database hard disk or RAM? Anyone?
hard disk.
All right. Everybody has the same opinion?
It depends.
All right. Great. What does it depend on?
So not 100% sure, but I think the caches as a database could be RAM, and the other ones could be. It depends on the architecture of the database itself. That's my understanding.
So you're saying cache is RAM, but okay. So if I draw a cache, let's say here. So this is RAM based, but this is HD based, right? Or can this be RAM as well?
This could be RAM as well.
Okay, great. Okay, cool. So a lot of people have this. I don't know why I'm hearing echo on my own thing. But... All right, never mind. So a lot of people have this basic thing wrong, that it's just hard disk, right? It's not. It depends a lot. And this is what we are going to unfold today, that there are a lot of databases which actually have RAM as well. Inside, I mean, like, not as a cache. Cache, I agree, is RAM based because you want quick. We'll discuss that as well as we go, right? All right. So let's discuss that right now. Before I go into the database indexes. Indexes is basically we have discussed all of the things that this fetching and storing is what we want to do in an efficient way, depending on the parameter requirements given to us, right? Maybe we want our fetch to be faster. Maybe we want to store quickly, right? Depending on that. And depending on that, we decide on what kind of database, and depending on the query, also we decide on what database to choose, right? This is the basic idea. Firstly, let's discuss the hard disk and RAM part. Okay. This might sound like very trivial to some people, but I do want to discuss this quickly so that I can use it in my like after 5 minutes, I want to use this information. Okay. Why not use RAM, or why use RAM? Let's discuss both of the things.
RAM is expensive. Like I'm
This is
just,
a disadvantage, right? Yeah. Okay. Expensive. So why not?
but it's also like a con in terms of like, if you want it cost efficient as well, then RAM is expensive.
Yeah. Yeah. True.
Yeah.
Not
Right.
persistent.
It depends on your
Durable. Yeah. So durable. Somebody said.
Can lose data if something goes wrong.
So persistent, durable, same thing, right? Right. Yeah. Great. Advantage.
Faster.
Quick.
Faster access.
Right. Simple stuff. Okay. All right. So ideally, we want to use RAM, right? I mean, except this expensive and the durable part. If we can solve this, we want to use RAM, right? Ideally, right? Okay.
Is it also limited? Like RAM could be limited, right?
Perfect. Okay. Great. Limited is because of the expensiveness, kind of. That's what the idea is. But I understand. Understand the point.
Yeah, and also like for distributed as well, it's challenging to like sync across.
Why is hardness not challenging?
Yeah, the same concept would apply there.
Right? So that's not a disadvantage from the hard disk, because we are discussing the advantages and disadvantages from the hard disk part, right? So these are good enough. Okay. So RAM is not durable, power off, data poof, right? Gone. I do want to discuss the durability part right here. Durability can be solved. Or should I? Okay. Let's firstly go forward with this. I'll come back to the write ahead log. Again, this is a lot of theory. Consume it. We will use it later on, and you will see why, right? So write ahead log, let's discuss it. So write ahead log, basically, as the name says, is a hard disk where we only write and we never delete, and we append. What I mean by that is this solves the durability aspect of the RAM. What we do is we have a RAM, let's say, and we use this WAL, which is a hard disk, actually hard disk. The way we write on it is we just append. So before doing any operation on the key value or anything here in the RAM, we write it first. We write here in the write ahead log. That's why the name write ahead log. We write ahead of writing to the RAM here so that it becomes durable. Whatever operation we are doing. So let's say I will write here change key 1 to key 2, the whatever, right? Delete up whatever I'm doing. Write all of this is just appended, right? We just keep on writing to the hard disk before we do anything to the RAM, and that solves the durability part of it. People understand what I'm saying? Writing to the write ahead log is O of 1. Why? Because we are just appending. Let's say our pointer on hard disk is somewhere here. People remember what hard disk looks like? There's a metallic disk. There is a, what do we call this? The spindle kind of, and it is pointing to some address. We are writing here, then we are writing on the next, then address, then next address, then next address, next address. This is what we are doing. So O1 directly. Are people aware of this hard disk thing? How hard disk looks like? There's a reason why I'm going here. Bear with me. I know this sounds out of the system design scope, but it will come. So people are aware of this or not? Okay, let me draw. So hard disk looks like this, right? We have multiple disks. We have an arrow, kind of, which is a read pointer or write pointer, whatever you want to call it, which is pointing to some address, right? This is what I'm writing at or reading at. So these disks, they move and we write on the next address, and then we write on the next address or read from the next address, whatever. If I have to read from here, then I have to move. Firstly, this goes vertically, and then I have to spin it to reach this point. This is a lot of work, right? Just yeah, this will make sense. So write ahead log is O of 1 because I'm writing right here. Then I'm writing right here. I'm never moving all the way or anywhere other than where I am at. I'm just moving to the next address, right? Why I'm mentioning this again and again is because, hey, I was using RAM for my fast operations, right? Because it was fast, right? This is what I was using as a database. But let's say, and I had this durability issue with it, right? To solve the durability issue, what I did was appended a hard disk, which we call write ahead log, along with the RAM. Before I make any changes to the RAM, I write here in O1 operation and then make changes. How it helps is, let's say power off, data gone, but this is persistent. I can recreate my whole RAM using this WAF. Make sense? What I lost was this separate O1 writing each time before I write to my RAM or read from RAM. I lost some. My latency got affected, right? I had to write here first before accessing the RAM, right? Why I'm teaching all this is actually used in databases. That's why I'm getting to, and we'll talk about this, like which database actually has this, right? So that's why I'm teaching all these concepts. People understand what I'm saying? We lost a little bit of latency. This is O1 though, but still, like we lost something. We lost some. Can the hard disk be corrected as a failure point? Absolutely, 100%. That's why we have maintain always a replica for this. This is a common system design concept to have replicas always. This is what we call single point of failure. Never have a single point of failure. Never. have a replica, at least one replica for everything. Good point is all the databases that are there today, they already provide it inherently, right? So you don't have to really, you have to show it. Like in a system design interview, you would say, hey, like this. Like, you'll show it like this always. Like have two databases. What this means is replica. But let's say whatever database I use, let's say a SQL database or a Cassandra or whatever, um, MongoDB or whatever, doesn't matter. They have replicas. But you really do need to show them. All right, good point. Right. So we always have another copy of WL, of course, because what if this gets corrupted? But the idea remains the same, that this is O1, let's say, and then this is O1, right? Oh my God. This is O1, this is O1, and then we write to RAM. So if RAM goes, I have my WAL, I just have to go over all the steps of WAL, create my RAM. But this is a very rare event, of course, right? Like RAM going away. It's not like every day it's happening. If it is happening every day, then you have some problem. But if happens like it's after a year, after 1.5 years, you're good. You have some backup, right? But what you gain is, hey, you have RAM, you have fast, your data access becomes fast. So it's a good idea. We want to use it. We have kind of solved the problem of durability, right? Honestly. So durability is not a concern anymore, even if we use RAM as a database. We have a HDD, of course, side by side, but HDD's purpose is not to store the data, but it is to recreate the RAM. That's what we are using it for. We are not using it to store actually the key value pairs in the HDD. We are using it to recreate RAM. This is what a lot of databases also do. Right? So we solved this. Expensive, we cannot solve. We have not solved it yet. The day we solve it, there's a lot of things gonna change, right? HD will really become obsolete kind. But we have not solved it. And limited is because of expensive, right? We are limited to the usage of RAM because it is so expensive. We cannot store all of our data, which is huge. And that's what I mentioned at the very starting of this session, that data has become so huge. It is impossible to store it in the RAM today because it is very expensive, right? We already have this fastness factor, which is the reason why we want to use RAM. Yeah, awesome. So this is what our main problem is, and we will see how a database actually kind of tweaks it a little bit and uses RAM side by side along with the hard disk to do exactly what we have just told. And this is what Cassandra is. I'm just giving you a hint about it. And that's why I wanted to discuss all of this. Right, but we'll get to this. Okay, so good. So far, any questions? This is good so far.
So how the data is getting loaded into RAM from WL when we revamp the service?
We would have to go over the WL like whole thing. So that operation is ON.
Yeah, it is.
That
It
is
is.
once in. Sorry.
Yeah, it is kind using computing power again. Like
The whole WL has to be read. The whole hard disk has to be read.
Yeah.
But that is 1.5. After 1.5 years, if it happens once, fine. That is what the downtime is. And in fact, that's why we have replica. I mean, not really replica. Sorry, that's not the reason why you have replica. We have to go over the WL to recreate the RAM. The replica was for if one WL itself gets corrupted. So that's why we have another WL. But RAM, we have to recreate. But that's a very rare operation, and that's why we say amortized, right? But amortized O1, right? That's why.
And so one more question here. While recreating RAM using WL, right? Do we always pick the latest value for the key pair, or because we just do right ahead, right? We don't go back and update values. So,
But how do you know that this is the latest?
So yeah, that was my question. So if there's a key that gets updated twice, how would we know that
That's why right ahead log stores everything. What it stores is like this. Key 1 value 1 has been changed to key 1 value 2. Then if something other happens, then same thing. Let's say key one gets deleted, right? This is one, this is one, this is two, this is three. So these are all steps. When we are recreating, we literally go to first step. We firstly write this in RAM. Then we do this in RAM. Then we do this in RAM. So all of this has to be done. So just steps.
Yep.
Right? Okay. I know this is a long procedure, but that's what we have come up with so far. That's the best so far. But yeah, it's still good, right? It's still good because general O1, but in the worst case, it's ON, and that is very rare, right? Makes sense? Okay. Nice. Let me just go through the what did I have for the. Okay, great. Let's say, so let's talk about indexes a little bit. We have kind of, again, WL will come into picture. We have kind of solved the case for writing in O1 already. What I mean by that is, even if my database, let's say, is a hard disk, is a pure hard disk, fine. Remember data is this hard disk, right? Spinning and everything, right? Let's say I give you this question. My requirement is only to write. I do not, I mean, I do read, but I don't care about the time complexity of it. What I care about is the time complexity of write. Correct? How do I get O1? Use it as a WA. Agreed? You just append everything you append. And while reading, you search for the whole thing. I'll give you an example what I mean, right? Maybe people are confused. So what my requirement right now is read, I don't care. That is ON. ON means the whole disk, right? Even if it is the whole disk operation, let's say I want to say, give me value, give me the marks just in this code in 10th class, right? Let's say I want to do this. I'm okay with going through the whole disk. But when I'm writing just spin this marks in 10 class 190, this should be O1. This is all I care about, right? So let's say again, I have hard disk. If I don't do anything special, if I don't use it as a WAL, if I use it as a general hard disk, I would have to find Jaspinder first and then edit Jaspinder's mark, because Jaspinder I might have written before as well. Possible, right? People are making sense. This is making sense, right? And that will cost me WON because I have to go through the entire list. I might find Jaspinder here. Agreed, right? But I care about this. I want this to be as low as possible. So clever way is just to append. You write at the end. Wherever you are at the end, just write. Just maintain what the end is. What I mean is like this is where the last entry was written. So write just when there's entry here. Now while reading, if you encounter multiple Jaspinders values, then the last value is the correct value. So your read complexity has increased, but your write complexity is just O1. So why I am teaching all of this is because these are all the clever hacks that databases use. So, and these hacks will come in handy when we have a particular question and we want to address that requirement. And then we'll say, hey, we can use it as this, because my write, I want O1. But it's a very rare case that I want my reads to suffer as much as possible, but my writes should be as quickly. This is a very rare scenario, but it is a scenario, and this is perfectly fine. Like you have already, with using hard disk as database only, I have achieved write in O1. Just my reads suffer a lot. If you understand this a little bit, like reads, Now there are multiple Jaspinder entries. There's not even one entry. So reads have really suffered because once I see Jaspinder entry and my work is not done, I might find a Jaspinder entry later on. Or what I can do is start from the bottom and the first entry I see Jaspinder. That is a clever hack you can do. But the idea is same, right? You might have to go over the entire disk. And that's why I'm saying read is O1. But write becomes O1. Is this point clear, firstly? Questions?
It is always an insert then.
Sorry, what?
It is always an insert to database.
Insert to database?
Yeah, when you say writing Jaspinder multiple times, so let's say I have one record with Jaspinder. When I'm writing a new record with Jaspinder, it's going to be a new record, another record.
Yes.
It's going to be a new
Yes.
record. It's not.
Because
we are not doing any updates. It's just an insert
exactly.
to database.
That's what write ahead is. Write
Yeah.
ahead is always a
Base
pending.
insert.
Always an insert. Exactly. You understand the reason also why, right? Because if I have to find an insert, then I've done ON.
Mhm.
Right?
Yeah.
Understand, no?
Even let's consider I'm using a normal hard disk. So even when I'm doing the same operation on a hard disk, uh, as you mentioned, WL require write ahead log is also a hard disk. So even the normal operation is going to be cost O of one if it is an insert.
What do you mean normal operation? If I have to, let's say Jaspinder is already present. Let's say Jaspinder is already present. And now the normal operation means, the normal operation ideally should be, I am editing Jaspinder, right? I'm editing Jaspinder's key with some other value. This is what I ideally should have done. I should not have duplicate Jaspinder's value.
Duplicate, yes.
Right? I should not ideally. But here I'm saying fine with it. Deal with it during read.
Okay.
Because I want to improve my write latency, I just append.
Okay.
And that is the idea a lot of databases use for improving the write. This write ahead log, basically write ahead log is always the answer for improving RAM's durability aspect. So whenever you hear this funda, like, hey, RAM is not durable, you can make it durable by doing this write ahead log, right? By using a hard disk, basically, right? And it's used everywhere in system design, right? We'll discuss this multiple times when we do the questions, right? And this is what databases also. But we understand, right? So we have compromised our read, but we didn't care about read. We cared about read, right? Right? Okay. Okay. This was one thing. So we have solved our write problem, kind of. Write is fine. Write is O1. We care about reads now, and that is what most of the operation really are. And that's why this is not really a great solution. This can be a solution if write is the case, but that is rarely the case. Like write is what we really care about. That is not really the use case that we normally see. What we normally see is read queries and optimizing on that. Okay. This is what database indexing. This is where database indexing comes into picture. Database indexing is basically an instrument to improve our read speed. That's all. We are indexing somehow to improve the read speed. Remember this. Write, we have already solved. Right? There is no problem at all for us. Read is the problem, and we want to improve on it. So we use database indexing. Because you are good DSA students. So what can we do? I want to improve my read. I am coming back to the same thing that you told me, right? You guys told me. You said I have to organize data so that my fetch and store becomes easier. My store, I've told you already, is easy. I've done it in O1. Tell me, how do I do fetch? How do I make it easy? How do I reduce the latency for it?
We make a dictionary out of it. Like we index where the data is.
Perfect, right? So first point, done. Thank you, hash, perfect, right? The most obvious answer and kind of correct. So now people would assume that this is what we generally use. No, but we'll come to that why. So, but it's a good answer. Okay, making tree of the keys. Perfect. Why are we going to the tree? Why not hash? It was a question, or like because you said it, I just want to know the thought process, right? Like, why did we go towards the tree suddenly? What does tree gives us? Guys, okay, but same funda. Why? It is.
More like
You speak up. Um, Again, I'll keep asking questions. That's why I want you to answer. Let's speak up, right? Better search. How does it give us better search?
because
Price
you're
when-
going by character in a tree structure. Like let's assume like the character is a node.
Okay.
I'm not saying like it could be better. I'm just talking about the tree concept in general. Like
Whatever comes to your mind. This is the thought process because this is what happened like 60 years back, right? We wanted to improve the read speed. This is where the conundrum is. We came up with hash indexes first. Perfect. That's what people came up with. Then it had certain limitations, which we'll talk about. But just more ideas is what I wanted. Like, okay, what else? What else can we do? How
Price.
does and by the way, with your DSA knowledge, you already should know this if you scratch your mind a little bit. Like, why hash? Where will hash indexes fail?
collision,
Think about this, and you will come up with this answer. Yeah,
collision.
collision. Okay, but collisions we already have measures for it, right?
Okay.
We already have two things that we do: the linked list one and the multiple hash. Like we go on the next. We already have solutions for it. So collision, we have solutions, but space. Can people speak up?
Making a hash will always be an O((n) operation.
Sorry,
And
what?
then making a hash will always be an O((n) operation, right? So we'll be searching for multiple times.
Why is hash an O((n) operation?
Like if it's a string, right? You go character by character to form a hash of it.
But n, what is n here? N is just the length of the string, right?
Yeah, length of the string.
So n is not, n is basically L. N, but we were talking about n here was the whole diff, which is not n, right? But okay, fine. Okay, let's talk about it. Let's firstly go with hash indexes, right? Okay, hash indexes, great answer. So we discussed that. But we will understand what we're trying to do. We want to quickly access the read, quickly improve our read latency is what we want to do, right? So most obvious answer is always hash. Hai? We know this from our DSA funda, right? Okay. So let's say I make so let's have some entries. Just spin the me and who was speaking here? Akshar. So we have these cores. Okay, this is in hard disk. I create a hash for it, right? So what I want to do is just spin this. I have a hash somewhere stored. Like Jaspinder refers to this address, and this address points here. This is what hash essentially is, right? Or ideally, right? Jaspinder gives us, we make a hash function on this. Hash function gives me some address, something which it points to, and this pointers to that point, so that I don't have to iterate over the whole disk. This is basic idea. Now think about this. Again, drawing the same funda. I am here right now. Right now it's pointing is somewhere it will be pointing to. Just spin. The query comes to edit Jaspinder's score or find Jaspinder's. Let's say find Jaspinder's score. I have stored my hash somewhere as well, right? It's on the hard disk as well. I have stored it. So I calculate my hash and it gives me this address. By the nature of hash, this address can be anywhere on the disk. Do you agree? Anywhere on the disk. And ideally, if it's a good hash, it should be very distributed, evenly distributed. This is what hash function. This is what a good hash function is, right? It should be evenly distributed. So ideally, if I'm here, I might. It is very random then, right? I might find my address here, where Jaspinder is actually stored, right? Which gives me this entry, or it might be here, or it might be here. So next time when I search for Malayas, which is me, it might be here. This means that I might have to still move all the way. My disk rotation has to be all the way again to find the correct entry for which I have to edit or fetch. People get it? What I'm trying to say? Hash indexes are a big no-no in hard disk. For this reason. Hash index based DBs will never be HD based for this reason. Because, again, I'm reading it. Hash indexes, by the nature of them, will be evenly distributed among the space that you have. The space is the disk. One hash will be here, the other will be somewhere else, the other will be somewhere else, the other will be somewhere else. It is not located sequentially. It might be, but it is rare. It is not like an array where it's sequential. If I find Jaspinder here, let's say, Malayas I might find here. So I might have to go through the entire disk just to get to the let's say my query is find Malayas' value. I might have to go through the entire disk. That is what I'm getting to. People understand this? That's why hash index no in hard disk, but a big yes in RAM for this very reason. And that's why we are in DSA, we don't talk about it often because we use RAM because we are computing, we are writing programs, we are having this memory stack stuff, and we are fine with it. We're fine with using hash base because we're not doing any HD based operations. If it's an HD based operation, it's not O1. It might even be ON. That's why the whole problem with hash. That's one problem, right? One big problem. HD is a big no for hash indexes. Don't do this ever in a HD. And that's why databases are designed in such way. Again, we'll discuss which databases and how they hack through this. Idea is no hash base for HD. Right? For RAM, it's fine. By the way, okay. If my data is not huge, just one second. If my data is not huge and I can get away with RAM is what I'm getting to. If I can get away with RAM, do hash index base, right? But at the very starting of this video is what I say, data has become huge, and that is why the problem really started. Oh, what is considered huge data? GBs of data. Or even, sorry, GBs is less even, sorry. TBs of data. GBs is too less. GB, we can still, I think in today's world, companies can afford to have, of course, RAM based if GBs was the case, but TBs of data. This is where we draw the line. We can't have RAM for TBs of data, too expensive. That's the basic reason. It's all about budgeting. It's all about profit. So hash base indexes suffer when they are used in hard disks. All right. Second point where, and this is where sorry, somebody had a question. Prasid.
Yeah, so like I get it for the hard disk, right? Because it has physical disk in it. But is it still true for SSDs? Because we still have a DRAM in that. So is it still slow?
No, it's good. But again, the same problem. We have not reached a point where SSDs are even cheaper. It's still expensive and it's still the case. It's still hold. Hard disk is the cheapest stuff that is there, and that's what we ideally want to use for our budgeting, but have good read latency still. And that's why all these hacks have come up, and that's why all these databases were there. like neither SQL nor NoSQL, use hash-based indexes still, because one is this, and the second point I'm going to explain. And that's why they use something else, which we will get to. But they all use hard disk. They all use hard disk. Like both of them use hard disk. Some use, one guy uses a combination of RAM and hard disk, and one guy is pure hard disk. That's the whole theory. But at the end of the lecture, it'll be clear. Right. One problem is this. There's one more problem which somebody should have said. I feel if you're doing DSA, there's one big problem, another with hashes, which is a DSA problem. Somebody has an answer or something that's striking. Because these are DSA questions.
Collisions.
What kind of read operation would suffer in a hash-based index if I have hash-based indexing? What kind of read operation can I not do?
If you have like similar kind of data, it will create collisions. So we'll have to hide it.
Okay, fine. Collision, I have to do collision maintenance. That's one fair point.
I think the range queries.
Wow, great. Thank you.
cannot do.
Okay, awesome. So people know about this? Range queries, right? We can't do range queries. What do you mean by range queries? So let's say if there is all this data, right? Jaspinder, Malayas. I'm gonna write, sorry. Handwriting keeps getting worse. Okay. So J M J L J J J K. And imagine these are the first characters of the name, right? These are my key. And this is my value, something. Doesn't matter. Now the question is, if the read query is like, give me all the values of the name starting from J. That's a common query. Give me all of this data for this kind of thing. That's a common query. I can't do this here in HashBase. I can do it, but it's ON. I literally have to go over. There is no way I can quickly find all of the J's because they're not located together. You see where I'm going? If they were located together, then then we can do something about it. And that's why we have another DSA thing, which you might be getting a hint of, right? If you have done your DSA, like what can we really do? And that's what databases do. So same thing, right? It's a parallel, right? But with hash, there is no way. I would have to go over each of the J's because I don't know where this J is. I would have to go over the entire disk. So when it comes to range queries, hash, again, no. So these are the main two problems that people had with hash-based indexes. If these two issues are not there for your requirement, use a hash-based databases, right? Just remember this point, because because in an interview, if the requirements are such where you don't need to do range queries, right? Where the data, where you just need to do this, right? Like your data can fit in a RAM. It's less. It's not in TVs. And there are questions like that, by the way. There are problems where the data is not in TVs, where you will figure out, hey, I can just use a RAM-based database. That's your answer, right? So start with here. So first, this is the starting point. Like, this is where you should start from and say, hey, oh no, I cannot use this because of this problem. Then I will resort to something else. But if you can use this, use this. But in today's world, range queries are very normal. So people kind of expect, and that's why I said neither SQL nor NoSQL are based off this hash thing, because range queries are so normal that it's just not a feasible solution. Till this point, everything is clear. Problems with hash, good things about hash, right? So simple point, if keys can fit in your memory, but whenever I say memory, it's RAM, right? if keys are so less that they can fit in RAM and it's not expensive for you. If there are no range queries, you can get literally O1 reads and O1 writes. Best solution ever, right? But generally that's not the case, right? You want range queries. This is what brings us to our next thing. So people, I think, already are kind of getting where I'm going. We have to organize this in a better way so that we can make use of something. So what is this hinting towards? Somebody just say the keyword so that I understand people are getting it. Anyone?
Maps.
Maps?
Partitioning.
Maps? What is maps?
No, I was just trying to say if we can group similar words together and make a set out of it, basically.
Set out of it.
Partitioning.
But how do we do the, like, if the query is give me all the names starting from J. Oh, so you are saying do a hash of this, but how do you store this data? Where is this data? Like, how do you? Oh, so you are saying J have this, but then this can be not just J, right? It can be so many things.
Yep.
How would you? So think of something simpler that we do, even if it suffers a little bit on the read complexity, because you of course they're going to suffer right now. It cannot be O1. That's what we are saying. We are saying we'll accommodate range queries by suffering some read latency, right? So what do we generally do? There's a thing that we do, right, in DSA as well. How do we organize data if we want to do this range query?
Order.
Tries.
We're going too far. Tries. I mean, you're right in a sense, but how does try help us? Okay. How will try help me?
Because you go from J, let's say for just Pinder, you go from J, then you have multiple nodes, A, B, C, D, then you go to A, then you go to S, and so on and so forth. Like basically, you can traverse that.
So what is this? So, okay. Okay. So what you're trying to say is, okay, this is actually one step further than what I wanted, but it's okay. So you're saying we have this, if I understand correctly. Then we have A to, let's say, K, L to something, N to S, S to Z. Is this what you're saying?
Yep.
Kind of, right? Makes sense. Oh, no. That's great. Right? Yeah. Essentially, okay, this is the right solution. But firstly, before this even I wanted to, because generally our mind thinks, no one thought of binary search. No one. No. Binary search is like the most common algorithm that we use, right? For before even going here, like for this, because the query is like that, right? When as soon as you see, I want all J's, so why not just do have
But
this data?
Data needs to be sorted for that, right?
Yeah.
Okay, correct, perfect. Okay, so that's where, but so you thought of it, but you said then, hey, data is not sorted really.
Yeah.
But then how come we have this? Here also data does not need to be sorted.
It is already while inserting itself, it is sorted in tries, right?
Okay, then why not binary search is my question.
We don't have any order while inserting the data, right? When we are trying to insert data into a try, it goes by order. So when we are trying to insert, when we are inserting data, so we are not maintaining any order. Let's say I have J, M, K, L, right? So next, if I'm getting J A, it goes to J, then A. It points to A. So when I'm inserting into a regular map or something in normal database, it's like a new entry. JA is a new entry. J is there, JA is there. If JAB comes, it's going to be a new entry. Somewhere it gets stored in somewhere. So in a try, it maintains that order where it starts from J, JA, JAB. So when I'm trying to look for the watts for the
And
J,
why does it not? I get it. Why does it not? Why cannot be maintained like this? Like what we do. Let's say I have enough spaces, so I start from J, and somewhere here is M, right? So my JAs are here, and my JBs are here. Like this is also the same thing, right? Like we are inserting at the correct point where JB would be, where I should find JB, where I should insert JB. I'm just making a point, like why not binary search tree, let's say. Why a try? Why not binary search? Is my basic kind of question. This is a hard question. I'm not saying it's an easy question, but my initial thought would have been like when I first started reading about it, my initial thought was use a binary search tree. Like why even go there? Like have so this is split into so A to Z is here. So I have my A to something here, and then same thing. I understand try is better, but then you have to tell me why. Because if you went directly to
Because
try, then you went directly to some other trees.
because I think in try retrieval is really cheap, right? Because
Why?
binary search you'll still have log n dynamic, right? But
Okay.
whereas try
Log base what?
and log n.
Base 2n, right? Okay.
Yep.
BST.
But in try, it's essentially of, I mean, length of the string basically. So O of n for each character, O of 1 for each character. So it's like less than a binary search, right? Because each child is of 26 storage points, or it has a limited set of array. So
you're saying it's not low?
yeah, that's what I'm saying. It's lower than a binary search, right?
It's not log, you're saying?
No, not log.
So if I give you a query, give me all the M. Give me all M. How do you do it? So you start from here, A to Z. Sorry, what was the which was this A to Z. So you go here.
Yep, we find
Then
M.
you go here. You know,
we
basically
go through
you have to go
all
here.
Yep.
Yeah.
And then within M, we'll have to find all that we
Why
need.
is this not log? This is log, right? Height of the tree.
Yeah.
But that's why I mentioned base.
Oh.
Okay. This is too much of a thread. So for the first class also. Okay. Basic idea being, let's talk about what we have discussed so far. So binary search tree can also be used, which is actually used in one sort of database. And this try-based, the different trees that you're trying to mention, they are also used in a different sort of database. So let me just speak it out loud. One we have discussed is hash-based. Both NoSQL and SQL had their variations with it initially. Both provided the hash-based solutions, not anymore because of obvious disadvantages that we have discussed. Fine. If those disadvantages are not there, if it's not part of your requirement, use this. This is the discussion that I'm having right now is very general, right? Like the two things that I'm discussing right now, all the major databases use a flavor of this, right? So Cassandra, MongoDB, SQL, whatever database, whatever known databases are there, they use one out of these three. Fine. That's why I'm saying it's very, I don't want to say exhaustive, but it's like 99% true. There might be some database out there which I'm not sure of, and there are multiple, like Google has their own. But idea being, this is what all the knowledge you need kind of for the interview. Hash-based, you already know now. You know the advantages, you know the disadvantages. Second thing is B plus trees. And third thing is, I know this sounds very hard to digest at first, but it's easy. That's like it'll grow on you, right? So after 2 weeks, as I said, you'll be like, hey, okay, we'll use a LSM tree. So this is LSM tree plus SS table. Hey, just remember this. I'll explain what this is, but just remember, right? So there are hash based, there are B plus trees, there are LSM trees plus SS table, right? Every database you can just search out, like search on Google. Cassandra is LSM tree based or B plus tree based. None of them are hash based right now, but maybe there are some left. And Google will give you an answer of which it falls into. MongoDB is which one out of these, or whatever database, whatever your favorite database is, you can search kind of, right? Like it should fall in this if it's a known database. All your SQL databases also, by the way, right? They should fall in one. Most of the SQL are these, by the way, and most of the NoSQL are these. But okay, that's for later. So hash base, we had obvious disadvantages. B plus trees. There's a theory about what B plus trees are, and it's some. Okay, firstly, let's discuss. We all know BST, right? Anybody who has no idea what BST is? Anybody knows BST? It's okay if no, if there's someone who has no BST, then I'll send a video, right? That's why I'm asking. People know, people read about BST? Okay. The problem with BST is, again, the same problem that we had in hash and HD. Again in HD. And that's why we don't read about other trees that much in our DSA. And we are only satisfied with max with self-balancing trees. That's the max that we do go. Like we go BST, we go tries, and then maybe red-black trees. Those are the self-balancing trees, but that's the max limit where we end our discussion in DSA, because we are dealing with RAM. Now the question has kind of changed. Question is, we are dealing with hard disk, and in hard disk, the problem is, and I think you can already kind of see when I draw this. This node, let's say, is A to Z. This is whatever, A to M. This reference node can be anywhere in the hard disk. The same problem that we had with hash. The address can be anywhere. It's a link, right? You again might have to traverse the whole hard disk. And it's the same funda. That's why BSTs also fail. This is one reason, by the way. After this class, I'll share a whole document on, it's a heavy document, but it has some points why BSTs are not good for hard disks. And that's why they're mostly used in RAM. Because in RAM, again, this access is O1. Direct access, random access, right? But in HD, it's not. And that's why whenever we do HDs, we have separate trees for it. And that's where B plus trees comes into picture. This is one of the main fundas. So remember this. I don't know when it will be asked, but if it gets asked somewhere, if you have to explain why not BSCs. So in HD, this link, if it's random really, you might have to traverse the whole hard disk, and that's an ON operation. That's a big no-no. You want something less than ON, of course. Otherwise, what is the point? Why are we even doing all of this? Just store data randomly. Okay. So when we do B plus trees, and B plus trees are very similar to B trees, this is a brief read, and we can discuss this in our next class tomorrow as well. Like if people want to know more about B trees, I can have a whole detailed thing about it. But I'll share a document about it, what B trees are. Essentially what exactly was said here. Very similar to trie-based, very similar to, but one good thing about B plus trees is this next reference node is like right next. That's what the idea is. So in HD, when it's stored, you don't have to iterate the whole thing, right? You don't have to iterate the whole hard disk. It's very optimized towards hard disk. That is one big improvement over BST. There are other problems with BST as well. One problem I can mention right now. B plus trees are, once again, B plus trees are not binary. B doesn't stand for binary. B plus trees are what we call actually M-way trees, but you don't need to remember this. But the idea being that there can be multiple nodes here, not just two, like binary search. Why is it a problem? If we just have two nodes, we get the time complexity as log 2n. This 2 comes from that bifurcation, right? I have two choices each time. Now, the time complexity is log mn. I can quickly make in my next node itself, in my next level itself, I have eliminated multiple. Let's say this is what I wanted to find. I have eliminated multiple of those, multiple things, and I quickly am reaching to my point. People are getting what I'm saying? Okay. So that's why B plus trees, like you want at least a try kind of thing. That's why the idea is. You don't want log base 2. You don't want your height of the tree to be big because it just is increasing your time complexity. So that's another thing. Why not binary search tree? Why not binary? Okay. That's why we resorted to, and we'll discuss more about B plus trees and B trees tomorrow again, just a little bit more detail so that I want people, as I said, like level 50 already, right? So I want people to consume it, absorb it, and that's why I'm skipping over a little bit some things because so that people can read and come have some mindset tomorrow that okay, I know a little bit about B trees. Okay. So B trees were introduced. Great points are range queries are good now, right? Although the cost is read complexity has in log n, right? Log mn, right? Depending on the bifurcation. But what about write? Think about write a little. This is where B trees really are not that great. Let me tell you why. So think, let's say I have to write. It's not as easy as just appending a node. If that was the case, then I might have very skewed things. I have to balance it. Think about this a little. Do people know about self-balancing trees? People know about red-black trees, AVL trees, have some information about it? Self-balancing trees is basically the idea is that you don't want a skewed tree. Because people remember from the course, of course, if it becomes skewed, then it becomes ON, right? Not log n anymore, right? People have this idea. Like if it becomes like this is just a linked list now, right? So it's ON, right? So we don't want this kind of behavior. So whenever we write, we have this added cost of self-balancing as well. Firstly, right? Makes sense? Writing is a task. Reading is okay. Reading is log mn, fine. I get it. We have definitely increased our latency, but not by ON. We are in the middle somewhere, log mn, and we are kind of fine with it. Log is still okay if it is balanced well, right? But it has to be balanced well. And when do you do the balancing? Of course, not at read time. You do it at write. Why? Because you don't want your reads to suffer. Why? Because reads is what we cared about. That's where we started our discussion from. Write, we had already solved. If write is what we cared about, we had already solved that. We just didn't have range queries, of course, but other than that, we had solved write. Write thing is easier. But reads is what we cared about. Our focus was on that. So log mn is kind of where we are at right now. But write, when we do a write in a B plus tree, it's a little bit more complicated because if I just add a node, then it becomes skewed. And also also not just if I keep adding nodes, let's say here, at some point I would have to bifurcate it. What I mean by that is I have to introduce another level, because the breadth might increase to a point where it doesn't make sense. I have to go through all of it. Let's say I can make up a case in it. Let's say the tree looks like this. We have node for each of the thing. What is the point of this? We're just going over each of them. People are getting what I'm saying though? This is a little bit complicated, right? Is there anyone who's not understanding? Am I rushing?
No.
No, I think I'm not rushing, right?
Yeah, you're not rushing.
Okay. So this is also bad. This is also bad. Every skewed way is bad. So you have to not do this. When you do a write operation, there are very clever algorithms written to optimize stuff. If you remember even the red black tree, they were like how you put the node back. You have to follow certain, if you remember, the right rotation, left rotation. So there's certain rules that you have to follow. So write complexity, even though it's log m, and I'm not saying it's on, but this particular stuff is not optimized towards write. What it is optimized towards is read. All the SQL, I'm again making a very bold statement, but this is what you have to do kind of in system design. You have to have an opinion. All the SQL based, because at that time, read was really the thing. At that time, I mean, like, okay, it still is, but let's say 20, 30 years back, we focus so much on read. All the SQL based used this B plus trees. They focused on read range queries. This is what the query of the day was. And we suffered from O1 to O log mn, and write also is log mn, but worse than log mn. We have to self-balance, we have to do some operations. That takes some time, of course. It might not be just log mn, pure log mn, but read kind of is. Okay. This is what B plus trees is. So yes, range queries, B plus trees. Read optimized, B plus trees. Keys, there is no limitation as such now because we're using hard disk. There's hard disk now. There's low limitation on the number of keys. The data is huge, great. Give it to SQL or B plus trees. So, okay, let me make the statement. All SQL based databases are B plus trees, but all B plus tree databases are not SQL. Is the statement clear?
Yep.
Okay, awesome. This is what I know. By the way, okay. Again, this is 95% true. 5%. There might be some versions of SQL that people have made. Hey, this is not a B plus tree, but the ones that you use, MySQL or whatever the known configurations that you use, all are B plus trees. This is basically right. I don't want you to quote me tomorrow that hey, I read somewhere that does not use, which can absolutely tomorrow I can make it, but basic ones, the ones that you use in your general company or wherever you use it, SQL based generally are B plus trees, and that's why SQL based are optimized towards read, and that's why whenever the requirement is read optimized is what you care about, mind should go towards a B plus tree based database because they are optimized towards read. Right? Writes are slower than, not of course it's slower than hash, but slower than the next one that I'm about to discuss. Slower than some of the NoSQL ones. So slower than LSM tree and SS table based solution. The name is, I don't know, overwhelming, but LSM tree is essentially a BST. So it's just the name is overwhelming, right? Okay. B plus trees is clear. Range queries, read optimized. Keys, you don't care about now. Like as in the data can be huge. Writes are a little bit slow. That's the only disadvantage. Read, Big yeses. Right? Next point. Before I move on, anything? No. Okay. LSM tree plus SS table. Sounds very, I don't know, but just remember it because you have to say it out loud. People don't say it out loud, and people just say, "Hey, we will use Cassandra." Why? This is why, right? This is Cassandra uses exactly this. That's why I keep mentioning Cassandra. But a lot of NoSQL databases use this, right? LSM tree is nothing but a BST plus self-balancing. SS table is nothing but a WAL, and WAL is always hard disk. Right? Remember this. So you already kind of know this. I'm just combining it now, combining all of what we have read. Fine. You know about BST, you know about self-balancing, you know about WAL. So this combination is what Cassandra is all about. This combination is what a lot of NoSQL databases are about. They are a little bit optimized. Remember this, they're a little bit optimized towards write. Okay? Because if they use this LSM tree plus SS table configuration. Okay. BST plus self-balancing. Why are we suddenly saying BST is okay now? Why do you think? You're muted.
Because BST has problem with balancing, so it was like not skewed.
BST has problem with balancing. It was not. No, but why are we? My question is, why are we saying we said BST is not good here, but suddenly we are saying, hey, let's use BST. Why do you think that is the case?
Because we were not using BST because it was not storing data in range base. So immediately will not find the data. Just the beside node could be on anywhere in the disk.
Okay, try to see this again. Why were we not using BST? Answer this now. Why were we not using BST here in the previous case?
BSTs can be skewed.
Even any tree can be skewed. Trees can be skewed. But B plus trees can be skewed. We did self-balancing to make it not skewed.
Yeah, so like LSM is self-balancing with BST, right? So
But B plus trees is also self. We have some balancing algorithm.
okay.
My point
The
is, why
search
were
is-
we not using BST in the previous case?
Log to log
Log
based
of an
dependency.
One was that. What is the other thing? The two reasons that I mentioned.
It is distributed, right? So we don't know where the next next
Hash,
node is.
same as hash.
Same as hash concept, right?
Yeah.
That means, okay, great. These are two reasons, right? Remember this. BST we did not use. There are many more reasons. These are the two reasons. I'll share a document that has many more reasons. These are the two reasons that are common. So why are we suddenly okay with it here? Because what we are going to do is we're not going to use hard disk. That's where the idea came. That's where NoSQL kind of thrived in the world. They based it off saying, hey, let's use a combination of RAM and ROM. That's where the initial point comes in. So RAM, we use it for BST and self-balancing. WL is always HT. So we use a combination of this. How does this help us is the main question now that I'm going to explain right now. And this is the last topic, by the way. After this, I'm done. I know this is heavy already, but yeah, 2 weeks are going to be like that. But after that, trust me, after 2 weeks, it's just you will speak out these things and that will solve the problem. That's it. So we use RAM based because RAM has certain advantages, but some disadvantages. And that's why we use a combination of them. We solve certain things by using RAM. We solve certain things by the hard disk, right? So in the RAM, now there's no need for B plus trees. We could have used B plus trees there, but there's no use. the advantage, the whole advantage of B plus trees. B plus trees really shine because they're optimized towards hard disk. If you're not using hard disk, there's no point of using B plus trees. I should not say no point, but there's very less advantage that you gain out of using B plus trees over BSTs. You can just use simple pure BST implementation, and that's why in our DSA we rarely encounter B plus trees. We just use BST, and most of the time that's fine. It just gives us log2n, and we're okay with it. So RAM, we have a BST, a self-balancing BST. So that means either a red-black tree. If people don't know what this is, you can read about it. But essentially, the idea is whenever it is about to become skewed, we do some operations so that it is not skewed anymore. We change certain nodes, we make it nice. That's the basic idea. You can read about it. So either of these two trees, BST, of course, right? What is the problem here now? If I just use this BST, I have solved the problem of so what is the problem here? If I just use a RAM,
not all data can be stored in RAM.
Perfect. And that's why HD comes into the picture, right? This is what we discussed initially, right? And that's why the WAL, the SS table. SS table is nothing. I don't even remember the full form now, but whatever. But SS table is nothing but a WAL, right? Multiple WALs, that's what it is. So we have multiple write-ahead logs, which can permanently store the data. So our problem is, okay, what is our problem? We have BST in RAM. We have the advantage of now when we write, okay, let's talk about write first, and then we'll talk about both the things, write and read. Right? This is our common operations, right? Right? Write and read, range queries, right? When I want to write, I only need to write in my BST. It's just adding one node. It is impossible that the key will not fit because it's just one node. And I'll make sure that my data is not full. How I will do that, I'll just let you know. But writing is super easy. RAM, fast. It's a RAM. It's not hard disk. I just need to go quickly, BST, search, log2n. But very fast. It's much faster than hard disk, right? We already know this. RAM is super fast. It's expensive, so all my data cannot be stored. That was the main problem, right? To solve that problem, what we did was intermittently, we will purge all the data. What I mean is destroy this BST, put it here in a hard disk to make the RAM free again so that we can write again. This is the whole funda, right? If you understand this, that's the main point. So we use a combination of RAM and HD. We use the advantage of RAM, which is fast. But the problem was that it was expensive because we have limited memory. We solve the limited memory by intermittently, whenever it reaches a certain point, let's say 75% RAM is full, we purge it, we destroy it, we write it in WAL. Beauty is, and see this now, we have a BST. Now, this question is for DSA. So if people have done DSA, you should be able to answer. What is the time complexity of me purging this and writing to WAL? And think about it. How do you want it? How do you want to write here in WAL? You want to write it sequentially. Why? So you can do range queries. What is the time complexity for sequentially purging this? Sorry, not purging this BST and sequentially writing it to WAL. Anyway, DSA.
O of n, right? Go through all the nodes.
O of n, right? This is sorted in order.
Yep.
Remember this. If people have some DSA knowledge. I understand if there other people who have no knowledge about this, then it's okay. I can explain this a little bit tomorrow. People know in order, traversal, post order, pre-order stuff, and why in order gives me the sorted list in a BST. And we care about sorted, by the way, right? Why we care about sorted? Range queries. Now I can do range queries there. If that was not the case, then it's a big problem. Then if the data is not sequential, then when I am reading through my WAL, I would have to go through the entire thing. Now I just do a binary search on it. Okay, a little bit more theory, right? But this is essentially the part. Write is literally log of n. You write only to the LSM tree, not to the SS table, ever. There's no need. Write is just an operation here. The only extra operation that you have to do right intermittently when the RAM becomes 75% or some value, that you have to purge this BST, put it in a WAL. That is the ON operation. So most of the times it's log to n, but in a very rare scenario, it's O of n. And n, by the way, is just the RAM data, not the WL data. You have to purge this data, put it in WL. So log n plus ON, but ideally it's log n, amortized log n, right? But very good, much better than the previous log n. Why? Because this is RAM. RAM is how, I don't know how many. I have to read it. Multiple times better than hard disk, right? So don't even compare one with the other. There's no comparison at all. It's greater than. The latency is really good, right? In RAM. So write becomes really efficient here, right? Now let's talk about the reads. For the reads, I firstly have to go through this RAM. If I find the data here, my read is fast. But of course, because RAM cannot fit everything, so I might not find my data here. And that's where read starts to suffer. Now I have to binary search on this. If I don't find it here, then I have to binary search on this. Why I have multiple WLs? Because you can have one WL as well. That's okay. Right? I can explain why we have multiple WLs. But imagine this is just one WL. Right? This is just one WL. I have to binary search over it. That's the idea, right? There's no other way. Right? So there are two operations now. I have to firstly go over this RAM for the read. I have to read it from here. If I find it, my read is good. Great. But RAM is super expensive and very limited. So most of the times I might not find it. Most of the times I would have to go through this WAL binary search. Then I'm back to the login, right? And hard disk. So my read has an extra step now. My read, if I find it here, which is very lucky, by here I mean the SS table, sorry, not SS. By here I mean the BST, the LSM tree. If I find it here, great. But that's a very rare scenario. I cannot. This is a good case, but that's not how we calculate our time complexity. The average cases we might have to go over WAL, right? And in the average case, basically, so what we're doing is two-step process. Firstly, go over the RAM, then go over the WAL. So I've added some complexity to my read. What I've improved on is right. This is where I want to end the thing. I just want to repeat. Here also, keys do not need to fit in the memory. What I mean by that is, like we have RAM and HD. I have unlimited HD. If I keep on purging my RAM and putting my keys in the WL whenever my RAM reaches the end of it. So what I mean by that is, like, data does not have to be limited. I'm not like hash based RAM where I was limited, right? It's okay to have huge data. I can still use this because I have the HD as my backup where I can do a binary search. So keys really can be huge. Dataset can be huge. Faster writes than what? The B tree based, right? People get it. Slower than hash, of course. This is nothing better than hash, right? But hash has its own problems, as we know. Range queries is impossible in hash. not impossible. It's ON. Okay. Here, range query is possible. Tree, and then binary search tree. Binary search tree and binary search. Binary search in the WL, and BST you already can do range queries on. You already know. Right? So range queries is possible.
So can
Okay.
we say? So can we say this is the reads are slightly worse than B plus trees here because we are doing multiple binary searches here.
Exactly. That's the perfect answer. This is what my opinion also is, and this is what I base. And I don't want to say I'm correct only, but but the idea is this is a solid opinion, and this is what the system design interviewer will expect, kind of, right? Like your opinion should be based on some theory, and this is the theory behind it. Why LSM tree and SS table are more optimized towards write than reads, and that's why if your requirement is such that you care about writes slightly more than reads, prefer this. Make sense?
So other than Cassandra, which all databases uses this?
A lot of NoSQL. I have to read now. I think MongoDB doesn't, if I remember correctly. But if you search for a lot of, I am most familiar with Cassandra because I use it. But just search for it. NoSQL, I would say a big percentage uses this LSM tree. What is the other database that we know of? NoSQL. Let's say Neo4j's graph base. So let's not go there. These are the special kind of things that we don't want to. We'll discuss Neo4j, by the way, but not right now. DynamoDB. What is DynamoDB? Must be one of those. One of the either it's B tree based or it's LSM tree based, depending on what it is optimized towards. So if you search B tree or LSM, let's see, is a B tree based. So DynamoDB is B tree based, right? So this thing, even it's a so RocksDB is there, which uses LSM trees. I yeah, RocksDB exactly. Okay. So
it's not hard and fast that NoSQL databases are
no, not at all. That's what I said. The other way, right? So the only theory is write optimized LSM, read optimized B plus trees. Now databases choose which way they want to go. Either they use B plus trees. SQL databases, most of them use B plus trees. That's what initially how it started. So B plus trees database predates LSM. LSM is more recent, right? So so it's not like a hard and fast rule. That's why I say any database can choose any of these, but it will be 95 or 90, even more than 95% are these, except special cases like graph databases are there. They are special, right? They are used for certain special cases, and we'll use those databases. I'll only discuss when I discuss problems. When I discuss problems associated with them, like there's a specific reason for using graph database. But if the specific reason is not there, you will use one of these, either LSM trees or B tree. Now you choose whatever you want to choose. Like you choose Cassandra or you choose RocksDB if you're familiar with it. I am more familiar with Cassandra, so I will urge you to also use that because my theory will be around it. Like I know internals of Cassandra, so I will quote them. You know what I mean? So you can quote them over there as well. This is how I would go. But if you have a preference for what DB you use and you know the internals of, you go. Like you do your thing.
The basic idea is if write is a priority, then use this, and if read is a priority, then use the
But you should know the theory of behind it.
Yeah.
Because once you say it, you should know why. Is my point. A lot of people just have crammed it, and a lot of people have these wrong cramming things as well. Like I've heard this. I mention this every time. Like people say that SQL databases can be should not be used when the data is huge. You might have heard this as well. I'm not sure how many people are into this sort of stuff. If you are, you must have heard this. Hey, SQL database cannot be scaled that well. Like this statement is very common. It's false. Honestly, it's false. So I would not say it is an interview. No. YouTube uses SQL database, which is their own word something, and it's a SQL database, and they have tons of data, and they have scaled it very well because they use this special database which optimizes for scaling but uses SQL in the backend, so uses B-tree based database because read is what they wanted to do, and they didn't want to go for NoSQL, which uses LSM based, which are more optimized towards write. You see where I'm going? YouTube generally we are viewing more, right? So they wanted a database which is read optimized. So they wanted to go at that time. It was SQL was available. So basically, what they did was they created their own database, which is called. It starts from V. I'm forgetting the name. So they have their own version of the SQL database, which is very optimized for scaling. So they did it. So SQL database can be also scaled. This is a false statement which people claim that SQL database cannot be scaled. Okay, we are going way ahead of the point. 7:13 already. I want to end. Let me stop the recording and then I'll take some questions because I don't know what